This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you. Refresher on the principle of relativity. Galileo, using one of the fastest means of transportation available to him, made a thought experiment about sailing ships and how physics tends to stay the same even if you are on a fast-moving ship. For example, you and your crewmates can play a game of cards inside the cabin of a ship while you sail at its top velocity. And the cards remain on the table, omitting any sloshing. However, to people that can see you playing cards from the shore, the cards, say as you fold your hand, dropping the cards straight down, appears to move at great speeds from where they used to be to meters away in the direction of the ship's movement. What appears to you as the cards falling straight down appears to people on the shore like you tossed them across the sea such that they landed where the table will be, not where the table was. Galileo summated that the laws of physics hold good for objects in constant motion, that the motion is relative, that to the crew on the ship, the people on shore are moving, and those people on shore say the people on the ship are moving, and aliens watching the Earth floating past think that both of you are moving. There is no universal stationary object which all other objects are judged against. There is no center or stationary. Everything is stationary to their own perspective, and everything else appears to be in motion or stationary according to their stationary position. Einstein's special case of the principle of relativity is no different from Galileo's in principle, namely that Einstein's two postulates fall in line with the essential nature of the original principle. The first postulate states, physics is the same for all observers. Just as Galileo showed, the second postulate is actually a derivative of the first, being that it states, the speed of light is the same for all observers. The second postulate comes from the first postulate, and from the work of James Bradley and James Clerk Maxwell. Bradley first found that the speed of light was the same no matter what star he measured. No matter which direction the Earth was moving, light was always the same speed. Maxwell showed that the speed at which the electric field interacts with the magnetic field is identical to the speed of light. Einstein, through his work, which we will explore here today, tied the two together and stated that the physics that is the same for everyone is a physics which uses light to interact, and therefore, no matter how fast or motionless you are, if you exist, then light is moving at the same speed as it always is. For physics to be the same on a train, which is moving at its top velocity on Earth, or a lab on Earth, which is spinning and orbiting the Sun, or a lab which is stationary in the Sun's frame of reference, which is orbiting the Milky Way's center, then the speed at which these atoms interact, the speed at which the atoms of brain neurons must interact, must be the same for all observers. For this, Einstein needed to show that 1. Photons are light, and photons interact with material as packets of wave energy. 2. That material which the photon interacts with are made of atoms, that atoms exist. 3. That Maxwell has a Galilean relativity problem, and that problem is solved by understanding what must physically be observed by people outside the moving frame of reference. And 4. That mass and energy are equivalent, which is the consequence of 3. All of which Einstein achieved in 1905 at the age of 27. The first paper was on what is called the photoelectric effect, which establishes that light comes in wave packets called photons, and that the energy of a photon is quantized. Newton, 300 years earlier, showed that light was heating up objects, not just shining light and color. That materials absorb light and reflect color and heat. Einstein showed that the absorption of light at certain frequencies could cause the material to emit electrons. Before Einstein's photoelectric effect experiment, scientists in electromagnetism thought that electrons could be emitted through a continuous buildup of continuous light waves, such that the material would continue to absorb energy until it filled up to a limit and would then emit the electron. The experiment proved that this is not the case. Light of a certain frequency, which is lower than the threshold for the emission of the electron, never emits the electron, no matter how long you wait or the intensity of the light. However, a low-intensity, short burst of light at the correct frequency can emit an electron. Einstein thus showed that the best description of a photon is that it is a discrete packet of energy, a quanta of energy, not a continuous wave through space. This we will come back to when we get into quantum mechanics in later videos. In the second paper, Einstein modeled Robert Brown's pollen in water observations to show that the random motion of the pollen was caused by atomic interactions of water molecules, which at various times, interacting in various ways, interacts with the pollen in different places, in different degrees, and the resulting atomic forces physically move the pollen, resulting in what appears as the pollen randomly walking around the petri dish. The third paper, Einstein showed that Maxwell's equations of electromagnetism was not matching up with Galileo's principle of relativity. To understand this, we need to get a bit more acquainted with Maxwell's equations. The equations known as Maxwell's equations were not created by Maxwell. Maxwell simply compiled a list of experimental equations, and that list was a lot longer and a lot scarier looking than the set we know today. The set we know today was actually provided by Heavyset's simplification of Maxwell's compiled list. Inside two of the four field equations, Gauss's law and Ampere's law, there can be found two constants. The constant inside of Gauss's law is epsilon naught, which is called the permittivity of free space, which is the capability for an electric field to permeate a vacuum. There is also the permeability of free space, which is denoted mu naught, which can be seen appearing in Ampere's law, and is how permeable space is at letting magnetic fields flow through it. The permittivity value can be determined by using Coulomb's law, where the charges of two objects are known. The force between them is known, and the distance between the two charges is known. I have covered how Coulomb first found the value for the permittivity of free space in the History of Electricity video. We can just say that if two balls are given a charge of electricity, then they will exert a force on each other. The strength of the force will depend on the amount of charge and the distance between them. The constant that Coulomb used was necessary because the environment in which the charges interact makes a difference, even in a vacuum tube. The product of the charges, divided by the distance squared between them, is not the exact force. The permittivity is a constant of proportionality between the electric field in a material to the electric displacement in that material. And in this case, the material is the ether, or free space. You can have, as an example, the permittivity of water as well, which is not very permitting at all. If you take two metal plates and you charge one to be negative and the other to be positive, an electric field will form between the plates. If you place water between the plates, the electric field in between will decrease. If you remove the water and air between the plates, all that is left is the little stuff, which we find to have a constant property value of 8.854 times 10 to the negative 12 farads per meter. The permeability value is a proportionality between magnetic induction and a magnetizing force when forming a magnetic field. For example, the permeability of iron is very high and will become magnetic in the presence of a magnetic field, whereas wood has a very low permeability and can ignore the presence of a magnetic field. The wood is not permitting the magnetic field. The iron is permitting the magnetic field. The little stuff of the ether, or free space, has a property of permeability which is equal to about 4 pi times 10 to the negative 7 Henry per meter. Maxwell found that a time-varying electric field acts like a current and applies to Ampere's law, which says that a magnetic field is created. By applying this to Ampere's law, the equation becomes mu naught times epsilon naught times the time-varying electric field. This leads to a wave equation, and wave equations have waves which have velocity, and therefore Maxwell was able to find the speed of the electromagnetic wave, using only these two constants which are experimentally demonstrated. Maxwell found that the electromagnetic wave happens to travel at the same speed that light was being experimentally demonstrated to be, and was therefore able to link electromagnetism with optics, showing that light is in fact an electromagnetic wave. This explains why the tests of the speed of light through an ether demonstrated a constant speed of light, no matter the motion of the observer or the source. The wave speed of light is determined by the properties of the free space, or the ether if you prefer. Here then we can add that the constant velocity of light is the result of the electromagnetic properties of the ether. Maxwell's electrodynamics has a Galilean relativity problem as shown by Albert Einstein in the introduction of his 1905 paper on the electrodynamics of moving bodies. Let us explore this quickly using a simplified electromagnetic law, which states that an electromagnetic force is created by an electric force and/or a magnetic force. If a charged particle is displaced by this force, the displacement must be caused by one or the other, or a combination of the two. An electric force is caused by an electric field interacting with the electric field of the charged particle. A magnetic force is caused by an interaction between the magnetic fields. We know from the History of Electricity Lecture 2 video, a magnetic field will only exist around moving charged particles, and therefore, the current creates a magnetic field, as does the moving test charged particle. A stationary charged particle does not cause a magnetic field, and therefore, a stationary charged particle cannot interact with the current-carrying wire's magnetic field. Einstein used this law to prove that there is a Galilean relativity problem with Maxwell's equations. Paraphrasing Einstein, he writes, "A copper conducting wire has no built-in magnetic attraction, as the wire has an equal number of positive and negative charges, making the wire neutral. Maxwell's first equation, Gauss's law, says that an electric field depends on the charge density. A net charge would mean no electric field, which means no electric force. Even if we hook up a battery and get the electrons flowing, the charge density remains the same, and so there is still no electric field, and therefore no electric force." Maxwell's last equation, called Ampere's law, states that a moving current does create a magnetic field. The Lorentz force law states that an electromagnetic force exists if an electric field exists and/or if a charged particle is moving with a velocity through a magnetic field. We currently do not have an electric field present, but we do have a magnetic field now. But without a charged particle moving through it with its own magnetic field, there will be zero force. Here Einstein points out that the relative motion of the objects in the scene would violate either electromagnetism or Galilean relativity. both of which are experimentally confirmed to exist. So there must be something wrong with our interpretation. If we put a charged particle in motion near a copper wire, from the point of view of the stationary wire, a charged particle's magnetic field is moving through the wire's magnetic field, and, therefore, a force is created. But from the point of view of the charged particle, the wire is moving, and it is stationary, and so there is no velocity of the particle, which means there is no magnetic field for the charged particle, and the wire is neutral, so there is no electric field from the wire, and therefore there is no force whatsoever. From this point of view of an object moving relative to the charged particle, the laws of physics have changed, and Maxwell's equations would need to be rewritten, up until they stopped moving with the charged particle, where they would need to return to the old equations. This would mean that relativity wouldn't hold for objects in motion, which is the only reason for relativity to exist at all. Something is wrong here. When the observer is moving with the charged particle, there is still a force applied to the charge, yet in this frame of reference, there is no force generated by an interaction of magnetic fields as the charge is not moving, meaning the force can only be created from an electric field. The only way for an electric field to exist in this reference frame is if the charge density in the wire was not neutral. The only way to satisfy electrodynamics and the Galilean principle of relativity at the same time is if space and time are relative, as charge is invariant and does not change with respect to motion. This is where the concepts of length contraction and time dilation are implemented into the principle of relativity. The only way to account for the forces affecting the particle would be if the charges in the wire are no longer neutral, such that there is a higher density of particles of one kind or the other in the wire, which will depend on the point of view you observe the experiment. From the perspective of a stationary charged particle in the wire's magnetic field, the density charge would come from an increase in the protons in the wire. Assuming the wire is solidly packed with atoms that cannot move, this effect can only be true if the lengths of the proton have contracted. This would produce a high density of protons in that region, which produces an electric field, which would interact with the electric field of the stationary charged particle, and therefore an electric force interaction would occur. The solution to Maxwell's electrodynamic problem can therefore be solved using a special case of the principle of relativity, which leads us into Einstein's special relativity. To understand Einstein's special relativity, we need to return our minds back to our bodies. We need to be the measuring device, taking in perceptual data or energy from the outside world, pursuing objectivity completely. Simultaneity, time, and position. Perception is based on simultaneous sensory interactions. The formation of the perceptual level is the result of neurons firing together, and therefore wiring together, caused by the energy received by the sense receptors. When a sense receptor receives energy from the external world, it activates, and that is the activation of a biological cell, which has similar physical requirements of the life the entity helps make up, and therefore it must consume energy to function, and then reuptake its source of energy to prevent death and to continue functioning for the next step. The activation of a cell causes the cell to become temporarily unable to activate again, equivalent to not being able to kick because your leg has just kicked and cannot kick again, it is at full extension. The cell takes a moment before it can fire again. When the cell is back to ready mode, it fires again and sends the exact same signal in parallel with all the other cells that fired with it the first time. Given enough exposure, to repeating simultaneous activations, patterns emerge in the cortex: dots, lines, circles, squares, triangles, etc., including patterns of motion, for example. The detection of a line in a column of cells, say A, B, C, D. The line was first detected by A and B, but then the column A was off, and B and C were on. Then B was off, and C and D were on. This impressionist-like detection of lines develops into perceptual detection of motion, either the motion of the object or the motion of us as the subject. An essential characteristic of a percept is the fact that it is perceptually constant. It does not vanish into thin air. It keeps its shape, size, color, etc. For an object to be perceived, it needs to be something that remains the same. It doesn't change over many reoccurring activations of sense receptors. And it needs to be occurring simultaneously to every sense receptor receiving energy from it. The perceptual level of cognition is based on simultaneous sense reception activations. This is what allows for classical conditioning in animals. The animal, or a small child, see baby Albert, is exposed to an object, and is constantly simultaneously exposed to that of a different percept, until the animal's perception of that object includes this other, unrelated percept. Say you have a speaker play a sound at the same time the object, a rat, opens its mouth. Even a grown adult put in that situation will be taken aback, wondering how it is that the rat made that noise. It would appear that the rat did make that noise precisely because it happened at the same time, many times, a series of simultaneous events. The formation of percepts comes from things that don't change in space or time, omitting the movement of the object or subject and omitting decay lengths of materials. Implicit in a percept is space and time. That thing over there at this moment, at this snapshot of sense detection. The perceptual observability of causality implicitly starts to provide this, then that. And those causal percepts come from experiencing one set of simultaneous sensory detections following another set of simultaneous sensory detections of an external simultaneous interaction of objects, aka perceptual awareness. When children learn about the science of time measurements, they learn that by measuring the amount of clicks on a clock an event took to go from start to end is how you measure time. Measuring time is an abstraction, an answer to the question, what would my senses simultaneously perceive at this simultaneous click of a clock? The concept of time is tied to the question, what would my senses simultaneously be experiencing if I paused somewhere in the causal chain of events? Time is the product of experiencing causality perceptually, experiencing the external simultaneity of subject-object interactions simultaneously with the internal simultaneities of sense detection and integration. When we view the clock to see the time, the clock needs to be visible, which means light needs to be coming from a light source, reflecting off of the clock and reaching your eyes unimpeded. However, we have learned how and why light takes time to travel. We cannot change that fact of reality. Light moves at a finite speed. So when we look at the clock, what we see is coming at us from the past. The light that immediately strikes our retina the moment we open our eyes to the clock face is light which had already left its source, traveled the space of the room between it and the clock face, reflected off of it, and traveled the space between the clock and your eye. Within a room, and given the speed of light being so quick, the time it takes for you to see the clock face will match the physical mechanisms of the clock, given its human mechanical scale, despite time having changed, and so, typically, you cannot see very far into the past. However, the same cannot be said of objects in space. For instance, from Ole Romer's work, we know that it takes about 8 minutes for the light of the sun to reach Earth in a straight line. So if the sun were to magically vanish, it would take us 8 minutes to notice. The research of this ether that light was traveling through to get from the sun to us led to the scientist James Bradley discovering that light always travels in that ether at the same speed. Further research was then conducted to check whether the Earth's motion, or something about the Earth, was causing it to only appear as if it were traveling at the same speed, through a process they called ether drag. This led to the scientists Michelson and Morley to conclude, through not finding any drag effect, that the ether drag hypothesis, also known as the luminiferous ether theory, was to be rejected. If the effects of the speed of light in vacuum is an illusion, it is not one caused by ether drag. The speed of light as a constant was proven by James Clerk Maxwell by showing that the speed is the speed at which the fields of electricity and magnetism interact. And therefore, nothing can be faster than the causal connections which allow for the existence of all observers. Einstein takes only 2 facts of reality to set up special relativity. 1. The speed of light is the speed of causality. 2. Physics works everywhere, whether you think you are moving or not. These 2 facts, and our fact about the sun's light distance from Earth, helps us set up a great visual of what must be true. The sun is 8 light minutes away from Earth, meaning it takes 8 minutes for light to travel from the sun to Earth. Now imagine a situation where Earth has 2 suns, and it is set perfectly between the 2 suns. We know it is perfectly in between because it takes 8 minutes for light to reach the Earth from both suns. Now imagine that we send 2 rockets off of the planet, one on either side of the planet, complete opposite, aiming towards the 2 suns. Finally, imagine that at some small time t, briefly after the rockets launch off, both suns vanish or explode or dim or brighten or the color changes, whatever, so long as it is a light effect which takes the Earth 8 minutes to notice. Are the events simultaneous to the rockets like they are for the Earth? Very apparently, they cannot be. For the rocket on the left side is closest to the left sun and sees that sun's change in less than 8 minutes, and sees the change in the far sun in more than 8 minutes, and vice versa for the rocket on the right. Therefore, what is simultaneous for the Earth was not simultaneous for the rockets, and therefore, if one's understanding of time is based on simultaneous events occurring with the hands of your clock, then time cannot be universal like Newton held. For time to be universal would require that all 3 observers, everyone on the 2 ships and everyone on Earth, sees both suns vanish or whatever at the same time, which would mean that light would have to reach the rockets, which are not in the center, at the same time, and at the same time that the Earth receives both simultaneously. This would mean that light would have to travel very fast for the far rocket, normal speeds for the Earth, and slower for the close rocket. This was the presumed position, which is ether drag, as the scientists thought it had to be the case that all 3 were experiencing universal time, and so the ether dragging effects of the rockets and the Earth must be speeding and slowing the light to make it appear as if universal time did not exist. After Michelson and Morley smashed the ether drag, the only conclusion left to draw was that what counts as simultaneous events to one person doesn't mean it's simultaneous for others. This brings us back to the solution to the Maxwell-Galileo problem. We said earlier, the only way to satisfy electrodynamics and the Galilean principle of relativity at the same time is if space and time are relative, as charge is invariant and does not change with respect to motion. We now know that velocity of objects must be relative to observers, as this means that different observers see the same events in space at different times. So we get two investigators, and they are placed in different frames of reference. One investigator is riding the wire. The other is riding the charged particle. Both investigators agree that 1. Someone is moving. 2. The particle and the wire move further apart after some time t. 3. Both agree that the speed of light is c. And 4. That physics is working. They are not exploding on-causally. Special relativity. The manner in which to apply these equations, known as the Lorentz transformations, is similar to applying the Galilean transformations. In Galilean relativity, we saw that the speed of a thrown object was added or subtracted from the speed of the object it was thrown from, in order to have our math match reality and conform to each person's point of view. If a man on the shore wanted to know why the sailor thought the ball was only moving at 50 kilometers an hour, he had to remember that the sailor forgot about the relative motion of the ship. So the man on the shore subtracts the ship's motion and gets the same answer as the sailor, and vice versa. Lorentz transformations make clear that the ether is basically a fixed quantum field and light travels through it at the same speed in all directions, and matter which interacts with that light also travels through it, but the light is only attached to the ether, so the motion of the matter does not change the speed of light. Because of this, you apply the Lorentz transformation by remembering that the sailor of the spaceship, which travels at the speed of 0.7 c, forgets about the relative motion of the ship. And so the man on the planet has to multiply the sailor's measurements of time and distance by a factor which keeps the speed of light constant. This provides us with the definitions of proper time and proper length. Proper time: the time that elapses in the frame in which events all occur at the same location. Proper length: the length of an object in the frame in which events all occur at the same time. Alice and Bob are our two investigators. Alice stands on a train platform, holding an extended rod affixed to a flashbulb in each hand, which she is extending a total of 2 meters apart, in an east-west direction. Alice, using her brain, fires a neuron signal which is to have both hands turn on the flashbulbs at the same time. The light which is emitted from the flashbulbs will reach Alice's eyes at the same time. As light must always travel at the same speed in the same medium, then the flashbulbs must be equally far apart from her eyes, and the lights, from Alice's perspective, can be said to be emitted simultaneously. Bob is on a moving train, adjacent to the platform. Bob is moving at 0.7 c eastward relative to Alice. If Alice is seeing both lights at the same time, then before Bob can see Alice at all, as the lights have not yet reached Bob, he uses his smarts and does the math. Since the speed of light is c always, since Alice has the two flashbulbs 2 meters apart, since Alice appears to be moving at negative v, then the light moving negative c must take longer to reach the left side of the platform than the light moving plus c reaches the right side of the platform. Therefore, if Bob believes Alice when she reports that she saw both lights, requires for Bob that the lights were turned on at different times. Bob would find Alice had to have turned on the east light first, then much later turned on the west light. Bob checks their math. According to Alice, the two light bulbs are 2 meters apart, and they reach her at a time difference of 0. So Bob plugs this into the formula. The difference in time between the lights turning on for Bob is equal to gamma times the velocity of the train divided by the speed of light squared times 2 meters plus 0. Since Alice is moving, according to Bob, at negative 0.7 c, Bob finds a time difference of light flashes must have been 6 nanoseconds apart. Bob takes the flash bulbs, and they repeat the experiment. Bob now sees the light reach him at the same time. So what will Alice find when she checks her Mathin diagram? When Alice has the lights, she reports that the lights reach her at the same time, 0 nanoseconds apart. And she did so because she pressed the buttons at the same time. Bob argues that Alice must be mistaken, that if the first statement is true, then Alice must have triggered the eastmost light 6 nanoseconds earlier than the westmost light, as light cannot violate causality. When Bob has the lights, he reports that the lights reach him at the same time, 0 nanoseconds apart. And they did so because he pressed the buttons at the same time. Alice argues that Bob must be mistaken, that if that first statement is true, then Bob must have triggered the westmost light 6 nanoseconds earlier than the eastmost light, as light cannot violate causality. Alice and Bob both agree that the other's far light had to have been switched on first, but both say that they turned their lights on at the same time. One possibility is that the far hand experiences time differently than the close hand. Perhaps this is a brain effect. Maybe our right hands attempt to balance out neural length differences with a default 6 nanosecond delay. Unfortunately, this cannot be true, as the delay again shows up if we switch directions, and then it is the left hand that appears to experience that time delay. Still, maybe it is a brain effect, where the hand furthest from the forwardness is delayed for some reason. So Alice and Bob construct a new experiment. No hand switches to remove this possible bias. Instead, Alice and Bob fix clocks to their east and west walls. According to each investigator, they see their own clocks as ticking at the same time, reading the same time at the same pace. However, the other experimenter must disagree that their clocks are synced. Despite not being able to see the other person's results, as the light takes too long to reach them, they know that the light that traveled in the direction of motion must have come from an earlier time, according to them, as the light from the back end takes longer to reach the investigator in the center. So both investigators know that their clocks appear to read the same time simultaneously, but they must also know that since one or both of them is in motion, then the light moving in the same direction as their motion must have been emitted earlier than it would appear. And therefore, if they approach the clock on the back end, they would see it speed up as they move towards its proper time. So the clock in the front is actually behind, and the clock in the back is actually ahead, such that the difference in distance the light needs to travel to reach the investigators balances out to appear to arrive at the same time. This is because light travels through the quantum photon field, or ether, as opposed to being a type of object that experiences time and space. Light is not contained in the ship like the air and man and ball and flies and fish were. This clock setup is merely another example of the relativity of simultaneity. The lights coming from the flash bulbs or clocks were emitted or reflected at different locations at different times. A weirder effect occurs when the two investigators, within their own frame of reference, record the same time, but based on the travel distance of a mover, the other must calculate that the other's clock is moving further. So if they are recording 1 second, and you know it traveled more than 1 second amount, their clock must be slow. One of the thought experiments that demonstrates this is called the light clock, which is a perfect mirror box that has a trapped photon inside, such that the photon of light bounces up and down in the box, and each time the photon does a number of bounces, it counts out the seconds of a normal clock. As a simple example, 1 second may be counted when the photon does one complete trip from the top to the bottom and back to the top. In reality, such a clock would require millions of bounces to count 1 second, as light moves at 3 × 10⁸ meters per second. So if the box were half a meter tall, then 1 complete trip would be 1 meter. And so to count 1 second would require 300 million complete trips, or 600 million minus 1 bounces. I have a different clock that we can use. It's our neurons. A lot of your nerve cells have a long cord called an axon, and that axon is insulated with what is called a myelin sheath. The axon is long, such that a single cell can reach far across the body to communicate its signal, and the myelin sheath helps to make that signal move faster. Together, the signal of touch can move at 80 to 120 meters per second. As most people are between 1 and 2 meters, a 100 meter per second signal can travel up and down the average person 50 to 100 times in 1 second. For a signal to be felt, it does not need to travel all the way to the brain. Some signals can be felt at the moment the signal reaches the spine, such as the knee-jerk reaction or reflex. So imagine Bob is 2 meters tall. His legs are equal in length to his torso and head, making his legs 1 meter long. As Bob moves along inside the train, which is moving at 0.7 c, Bob feels a pebble in his shoe. If we were to set up a neurology lab in the train and hook Bob up to an EEG machine to test his nerve impulses, we see that Bob's signal moves at 100 meters per second, or 0.1 meters per millisecond. So it takes 10 milliseconds for the signal to move from the foot to the spine. If we repeat this neurology lab in the stationary frame, Bob's nerves still receive the signal after 10 milliseconds. So we can say that Bob's nerves are constant. They always receive the signal in the same period of time, 10 milliseconds to travel 1 meter. But Alice is not convinced. Alice never got on the train and never saw the lab being done, but she trusts her colleagues would not make such a mistake. But clearly something is wrong. For when Bob was on the train, the signal that started in his foot traveled straight up his leg to his spine in 10 milliseconds. But his spine was no longer 1 meter away. After the first millisecond, the spine, Bob, and train had moved 210,000 meters eastward. If Alice calculates how long according to her clock it should have taken the signal to travel, given the motion of Bob and his train, Alice must argue that by her clock, it would have had to take longer than 10 milliseconds. However, Bob counters and says that from his point of view, it was Alice who had the nerve signal that took longer than 10 milliseconds to be received. Given that he has the lab equipment using electrical signals that move at the speed of causality, he argues that it cannot be wrong that it took him 10 milliseconds, whether his frame is moving or not. And he argues that it was in fact Alice receiving nerve signals slowly, and therefore experiencing time slowly, and therefore seeing him slowly. If relative motion affected the speed of our nervous system, we would never move, as every time we started moving with a constant velocity that is different from the stationary Earth frame of reference, our nerves would fail to function properly and we would die, unable to signal the heart to beat and lungs to breathe. There is only one solution that solves the conflict. Velocity is relative, simultaneity is relative, and now we also know that time is relative. We already found the math that will help Alice find the time difference. According to Bob, his clock says 10 milliseconds, so she needs to write the equation delta t prime equals gamma times delta t. Delta t is Bob's time according to Bob, 10 milliseconds. And when Alice plugs that in, she finds that it actually took 14 milliseconds. Since Bob thinks he is stationary and therefore gets 10 milliseconds, Alice accounts for his motion, just like in Galilean relativity, and gets that Bob's clock is actually ticking slow relative to hers, not that his nerves are speeding up. Bob cannot witness this because Bob, his nervous system, his clocks, everything at that velocity is experiencing time differently from Alice. But according to Alice, Bob's clocks reach 10 milliseconds after what is really, in the Earth frame, 14 milliseconds. Since velocity is relative, and velocity is distance over time, and time is relative, we have to ask, is distance also relative? We can check if distance or length is relative. Distance is length between 2 points, typically associated with velocity and the time it takes to get places. But distance itself can be represented with a static map, such that the time of measuring distance on the map would make no difference. 2 houses a mile apart remain a mile apart on the map, no matter how fast you move objects on the map, or what time of day you measure it. Therefore, if we want to know the length of an object, we can make it sit still, and measure its top, and then its bottom, at different times or days, but since it's not moving, that's okay. One of the issues with length in these cases is how do you measure a length when it's moving? For instance, when you have a map that shows 2 houses are 1 mile apart, it doesn't matter how fast you move toy cars on the map. The distance is the same. What if you move the map around very fast? Does the distance change now? As, by the time you have a chance to move your eyes to the other end of the ruler, the location changed, including the first end, which is no longer at the first house. We found that if an object is in motion, then the 2 frames of reference will argue over whether or not their clocks were synchronized or not, and this causes an issue in the agreement of length measurement. So if we want to measure length, human clocks and rods will not be very useful to us. Instead, we can use the properties of light to get what we want. Light always travels at the same speed, so we don't have to worry about whether the velocity is relative. Given that, Alice and Bob set up a new experiment. Alice and Bob fix a laser pointer at the back of their trains, and a mirror at the front ends. The laser is fired across the train length, hits the mirror, and returns back to the source at the back wall. The length of the train is therefore the distance the light traveled, and the time it takes to travel is the distance divided by how fast it traveled it. So for Alice, who is stationary on the earth at the train station, the light traverses the inside of her train without the train itself moving, and so the distance the light needs to travel is the train's length twice, and its change in time can be found by dividing the twice train length by the speed of light c. Bob disagrees because to him Alice is in motion, and Bob states that to him he is motionless, and her calculations are actually his, that it took his photons twice the length of the train divided by c. But Alice knows that it is Bob that is in motion, and so Alice does the math to check what is happening here. According to Alice, when Bob's train's back end lines up with hers, it fires a photon towards the front of the train. But the train is moving in the same direction of that photon, so the photon approaching the front of the train must travel the distance of the whole train, plus the distance the train moved in that time period. Once the photon hits the mirror and starts to return to the back of the train, the distance it would have had to travel would be the length of the train. However, before it can do so, the back of the train races up to meet the light, and so the second photon travels the length of the train minus the distance the train moved in that time period. She finds that the change in time of the moving train must be gamma squared times the stationary frame of L2 over c. If Alice used the relativity equation of change in time of one frame of reference for another, and she plugs in the equations her and Bob found, then Alice comes to find that the length of a moving train is less than the length of a stationary train. When we get Bob moving at 0.866 c, Bob and his train reduce in length by a half. Bob's 2-meter-long train is now 1 meter in length as he moves. Of course, to Bob, he is normal, he is not moving, and Alice is the one that appears to be reduced in length, in the direction of her motion, by half. Einstein's discovery that the Galilean principle of relativity had a special case, due to the nature of light, demonstrated that the principle of relativity said more than just velocity is relative, and showed that it also proves that simultaneity is relative, time is relative, and distance and length are relative. Therefore, Einstein used this discovery to show that Maxwell's electrodynamics does not have a relativity problem, just a Galilean relativity problem. By involving a simple parameter, gamma, Galilean relativity becomes more powerful, and can now deal with objects moving near the speed of light. Einstein showed then that the charged particle, from its point of view, is stationary. However, the wire which appears to be moving is reduced in length, and therefore has more positive charges closer together, and therefore the wire appears to have an electric field, which interacts with the electric field of the positively charged particle, and therefore is repelled away from the wire. This solved the Maxwell-Galilean relativity problem. Just like with the Galilean principle of relativity, if you assume it to be false, then you would have to accept that every event involving velocity would have two or more causal realities, such that to one group of people, the ball was thrown backwards, and to another group of people, the ball was thrown forward. Likewise, if you assume the special theory of relativity is false, then you must accept that two or more causal realities split from the event every time an object or photon moves. Without requiring the assumptions of many worlds, special relativity answers the question of what time and length mean to moving objects, and does so without violating causality. Since causality is the one big thing we really cannot violate, then the special theory of relativity must be accepted as true. The alternative is to violate causality or to form many worlds for each and every velocity. Let us leave off with a real-life example. The sun sends out high-energy particles that move through space at near the speed of light, and upon hitting the Earth become a bunch of secondary particles, one of which is called a muon. The muon is an unstable subatomic particle, which has a mean lifetime of 2.2 microseconds. Given the short lifespan of a muon, under regular Galilean relativity, the muon would decay before it can reach the ground. However, muons reach the ground all the time. Given the distance they have to travel from creation to annihilation, from the atmosphere to the ground, the speed and lifetime of the particle is too small to survive all the way to the ground. Calculations show that it would take 6.4 microseconds at its speed to reach the ground. So how are they doing it all the time? Well, the muon is traveling at 0.99 c. So from the ground, we would see that the muon's clock is slow and is ticking to 2.2 microseconds in what to us is actually about 10 microseconds. And to the muon, it appears that the distance between the atmosphere and the ground has reduced from 2,000 meters high to 280 meters high, so it can reach the ground in 2.2 microseconds. If time dilation and length contraction were not facts about the nature of motion, then nearly all of the muons would decay in the upper atmosphere, which is not something we experience. Let us review our list of principles. Existence exists. A is A. Consciousness is conscious. The universe is causal. The universe is full. Nothing is prior to the little stuff. The Galilean principle of relativity is valid. Light is an electromagnetic energy disturbance in the electromagnetic or photon field, which always travels at a constant velocity in the ether because of the properties of the ether. The special principle of relativity is valid. Next time, we will explore the principle of general relativity. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.